I'll go ahead and get started. Yeah, I'm really excited to be here today to tell you all about the work that I've been doing on our current state-of-the-art and next-generation measurements, specifically on high redshift clusters. I'll just say that this is work that I've been doing kind of on behalf of the Axis Galaxies working group, and if there's so much science going on in that group that I won't have time to touch on today, but I will just highlight that what started as a white paper has now been officially accepted for peer review. So if you're interested in what Axis can do on the general evolution of galaxies and clusters, then go ahead and please check that out. But I'll essentially limit my talk today just on the study of galaxy clusters. So this is a recent JWST image of El Gordo at a redshift of 0.87. If galaxy clusters are the most massive class of objects in the universe, then this is one of the most massive of the most massive, which you can essentially tell from this image that most of the mass contained here is actually within the dark matter halo of such an object and is invisible to us, but you can see in these very nice lensing streaks. But actually what you can see in this image, namely the galaxies, say the BCG or brightest cluster galaxy here, is only a fraction of the total mass of the cluster. And if you really want to see most of the baryonic mass that we can detect, you need to go to X-ray wavelengths. So Axis will be able to probe the intracluster medium of galaxy clusters. And so I will focus essentially the rest of this talk on the ICM specifically. And that's because the ICM is a direct probe of the thermodynamics and chemical state of massive clusters and groups. So these are the quantities that we really want to probe if we want to understand the physics of feedback at the cluster scale. So some of the questions that I'm most interested in and relate quite closely to Axis key science cases are: how do activity from active galactic nuclei and star formation shape the formation and evolution of these most massive structures? So a significant amount of my work has been to determine what we need to push studies of the intercluster medium to the highest redshifts possible, namely towards the period of cosmic noon between redshifts of 2 and 3, where the activity from AGN and star formation is really the most active and prolific. And so in terms of the observables and what we actually see as the effects of AGN feedback, particularly for X-ray measurements of the density, temperature, and metallicity of the intercluster medium, we really reveal two types of observational effects. First is the instantaneous effects of feedback. This can be seen, for example, in this image of RBS 797, a galaxy cluster to intermediate redshift about 0.35, where you can very clearly see beyond the core AGN two very large cavities on these scales of tens of kiloparsecs. And this is an instantaneous effect. You can see the effects of AGN jets and winds heating the gas, blowing it outwards, and expanding cavities. But because galaxy clusters are so massive, they essentially trap all of the baryonic matter that's ever been contained within them for all of cosmic time. And that means they are great laboratories for probing this cosmic tug of war between the overall growth of structure and the non-gravitational processes of AGN and stellar feedback. And so by making measurements of the intercluster medium at a variety of spatial scales and redshifts, you can scale these measurements and make direct comparisons between the high redshift universe and the low redshift universe to really test the effects of AGN feedback. With our current state-of-the-art, though, precise measurements of these quantities, particularly in profile, are generally limited to redshifts less than 1, where it's fairly straightforward to produce these types of profiles for density, thermodynamics, metallicity. For example, if you wanted to create density and temperature profiles of massive cool core systems below a redshift of 0.8. But as you move to higher redshift, these measurements become exceptionally more challenging, particularly for metallicity. So at high Z, typically what we've done so far is consider a number of clusters in statistical ensemble for both thermodynamics and chemical measurements, particularly at the largest radii of clusters, which can be exceptionally useful to us because with so many systems across a wide range of redshifts, this does give us strong insight into the evolution of the intracluster medium. One of those ways is looking at density and thermodynamic profiles of these objects, which can reveal the competing roles of gravity and these non-gravitational feedback processes as a function of radius. We understand quite well how a cloud of gas in a dark matter halo should accrete and grow and evolve over time. In the presence of AGN feedback, though, these processes can be disrupted. So in the upper right here, I'm showing a plot of the scaled density profiles for 10 galaxy clusters above a redshift of 1. And you can see beyond the cluster core, for example, in this lower right-hand plot, beyond the cluster core, we see remarkably low intrinsic scatter in these profiles, suggesting that clusters grow extremely self-similarly, even in the presence of AGN feedback. And so despite the dramatic impact these non-gravitational processes can have, averaging out over the large scales of galaxy clusters over their cosmic formation histories, there is a remarkable uniformity in how these structures grow and evolve. Another question that I'm particularly interested in and connects to a key Access Science case is chemical enrichment. That is when and how the universe was enriched with heavy metals. If we make measurements of cluster metallicity in the local universe, for example, on the left-hand side here in the Perseus cluster, we see a remarkably consistent enrichment of metals at a value of about 0.3 solar beyond cluster cores. And this is true within the Perseus cluster along different directions. We not only see this value of about 0.3 solar azimuthally consistent, but as in the right-hand plot, we also see this in the local universe from system to system. And this is not something that we initially expected to see, and actually caused us then to go back to simulations and forced to update them with fairly extreme AGN feedback. So as shown here in this plot, if we only account for cumulative stellar feedback that produces these metals within host galaxies, we cannot recreate the observations we make in the local universe. In order to that, we really need to crank up the AGN feedback in our simulations to reproduce this uniformity and high enrichment. But this has other implications that aren't just limited to the local universe. Shown here, comparing top to bottom in the presence of AGN feedback and then just looking at this cumulative stellar feedback, if we crank up the AGN feedback enough to enrich the ICM at large radii to this value of about 0.3 solar, this feedback must also have been going on at early times and suggests that we should also see this enrichment at early times. We call this the early enrichment scenario. Essentially, metals that were produced very on in the formation history of clusters was expelled by supermassive black holes at incredibly high redshifts, which then was allowed to accrete and well mix as the cluster was forming and accreting this mass. And so to test this theory in practice, we need high redshift measurements of the intracluster medium, particularly of their metallicity. And that's something that I've spent an extensive time studying. And still, even extending these measurements out to about a redshift of 1.5, we still see strong evidence for this early mixing and accretion of pre-enriched gas. So this, on the right-hand plot, the blue contours corresponding to the blue data points represent the evolution in metallicity counting from the local universe up to about a redshift of 1.7. And those bands are still consistent with 0 at just over the 1 sigma level, pointing to the fact that the ICM was still incredibly enriched at early times. And these types of measurements are exactly what we want to continue with Axis, because they'll allow us to, by extending to even higher redshift cluster environments, probe the impact of AGN feedback on the enrichment and when these activities were most helpful in enriching the ICM. But in order to do that, we need more systems and better statistics. And that brings us a bit to the limitations of our existing instruments. So at high redshift, above Z of 1, clusters are still extended sources, but they aren't particularly large. R500 is typically only about 1 arc minute. And that means that only Chandra, with its high spatial resolution, can really resolve gas on the 10 kiloparsec about scales that are required to model cluster cores and determine cluster morphologies. But that really is just limited to cluster cores. Because of the decreased soft sensitivity of Chandra, that's fallen about 8 to 10 times what it was at launch, we really can't probe cluster ICM environments at large radii with Chandra. You might think that this is a great point for XMM-Newton with its high soft sensitivity and larger effective area to pick up, which it does at large radii, but its significantly larger PSF both struggles to characterize then the cores of clusters and crucially identify and separate emission from contaminating point sources. So that means if you want a full spatial characterization of the intracluster medium at high redshift, you cannot do that with a single existing instrument. You either need to study these systems jointly with both of our flagship observatories, or you need a new instrument with high spatial resolution, increased sensitivity, and a low particle background, i.e. something like AXIS. But going a little bit more into our current state of the art, this is what a typical high redshift system looks like with the data that we currently have. This is SPT 2334, a redshift 1.2 cluster. On the left is a deep 100 plus kilosecond Chandra ACIS I observation. You can see right in the center the cluster core, fairly well constrained. We can well determine the cluster morphology from these types of measurements, and we can readily identify, localize, and characterize the point sources that are also in the frame. Moving over to the right, we see a shallower XMM observation, which, despite only being less than half of the observing time, reaches much further out in radius of the intercluster medium. However, if we resize or generate masks for these point sources based on the characteristics determined by the Chandra data, we see that they provide significant contamination. And if we only had the XMM data, we likely either wouldn't be able to identify or wouldn't be able to adequately model simultaneously the AGN when we tried to make large radius measurements of the ICM. And so this has led us to a regime that our group at Stanford has been developing over the past number of years, trying to forward model essentially everything we can about individual observations. So we've been developing observation-specific models on chip-by-chip basis for both Chandra and XMM-Newton that will enable us to simultaneously model our observations, characterizing simultaneously the ICM at all spatial scales, which is crucial as we extend into this high redshift and low surface brightness regime. And just a few of these considerations have been from actual sky backgrounds and foregrounds, like the emission from our Milky Way halo and the local hot bubble, as well as the cosmic X-ray background, or essentially point sources that are unresolved or undetected by Chandra. This is also the individual particle backgrounds, which vary based on the observatory, but also vary spatially on the CCDs of each detector, and also ones that get even further into detector and instrument-specific backgrounds and variations, both the spatial variations of the backgrounds, for example, the particles I mentioned earlier, but also any particular instrumental lines that need to be specifically handled, or in the case of the PN detector on XMM-Newton out of time events. But AXIS essentially brings us the best of both worlds. So taking this forward modeling approach and applying it to AXIS is really the only way we can produce spatially resolved profiles of the intercluster medium thermodynamics and chemistry that we need to probe feedback processes. And that's based on its spatial resolution, its increased soft response, and its low particle background. So again, bringing us back to the example of RBS 797 on the left, if we scale this cluster environment up to high redshift, redshift at about 1.5 and point Chandra at it for about 100 kiloseconds, we lose a significant amount of the structure and sensitivity at large radii, really only being able to see the cluster core. But if instead we point Axis at it for 100 kiloseconds, we recreate essentially the environment that we're able to see at low redshift, both the core AGN as well as these AGN inflated cavities on either side of the core. And these are the exact types of systems we'll be aiming to observe with Axis. So the current Axis observing plan grants 3 megaseconds of targeted follow-up to 30 high redshift systems between redshifts of 1.5 and 3. And I've done a significant amount of simulation work on the most massive systems expected at these redshifts to reveal the constraints we can get with Axis in imaging and spectroscopic studies, which will allow us to push further out in radius and redshift than ever before. So on the left here, I'm showing an example from XMM-Newton at a redshift of 1.3. Our current state-of-the-art suggests to us that we can reliably constrain cluster properties up to the point where our signal from clusters is about 10% of that of the cumulative background signal. And for this example, this caps out at about 1.5 R500. Transitioning that to Axis, we'll be able to push out significantly further, especially as we go up to even higher redshifts, potentially hitting radii of R100 or R50 out to redshifts of 1.5 or 2. And all of this is enabled by Axis's soft response. As we go to higher and higher redshifts, and notably cooler and cooler systems, the soft band sensitivity is absolutely crucial for characterizing the ICM. I've done a number of simulations of what happens if you start to lose sensitivity below 0.5, 0.4, 0.3 keV, and you lose a significant amount of your cluster signal if you start to lose this sensitivity. But with the nominal sensitivity in the soft band that Axis has, we are going to get some pretty exquisite measurements. So between targeted follow-up of these massive clusters and, say, megasecond log deep fields that should detect these early galaxy groups, Axis is going to be able to constrain the intracluster medium, generally their thermodynamic properties, to within 10%, even out to the virial radii. So while I've shown 4 bin profiles for these examples, Axis is going to enable us to go much finer, maybe 6, 7, 8 bins of temperature out to the virial radius at redshifts of up to 3, which is fairly fantastic. Bringing this back in comparison to our current state of the art, I'll highlight this example we're currently working on, ACT 0123, a redshift 1.5 cluster that currently has about 50 kiloseconds of ACES-S data, about a quarter of that in XMM-Newton. And comparing the left and right-hand images here, you see the broadband Chandra and optical images detailing a strongly concentrated and bright cluster core directly on top of the optical BCG, brightest cluster galaxy. This is the highest redshift cool core relaxed galaxy cluster we've ever detected. And these objects are incredibly interesting and valuable to us. They are spherically symmetric. They adhere most closely to our expectations and assumptions of hydrostatic equilibrium, making them fantastic not just from a modeling perspective in astrophysics, but also they are fantastic cosmological probes. But looking a bit more between the Chandra and XMM measurements of this object, ACT 0123 has a very peaky and symmetric surface brightness distribution, which you can see here on the left. And because of the instrumental PSFs between Chandra and XMM, the measurements peak 3 times higher in Chandra. All of that peaky emission is spread out instrumentally in XMM. But because of the decreased soft sensitivity of Chandra, measurements of the intracluster medium can really only extend out to about R2500, which is about half as far as we can extend with XMM-Newton. So as I'm showing here, we really need both instruments to correctly characterize the intracluster medium out to R500. If, however, instead of 50 kiloseconds of access, at Chandra, we had 50 kiloseconds of access, just in terms of raw data, we would see almost 50 times the broadband counts from Chandra alone, giving us full spatial resolution of the structure of the cool core. But it would also allow us to push out both in thermodynamics and chemistry out to the virial radius, giving us about 50% precision in terms of metallicity measurements. To place that in context, if you were to develop an XMM-Newton campaign at a similar redshift to constrain metallicity to this degree, this would be as good as something about 10 times as deep in XMM-Newton. And this really gets at the heart of these chemical enrichment and AGN timescales that we want to constrain with access, which we will finally be able to do at high redshift and large radii. So we know empirically, as you can see on the left, that both AGN activity and star formation activity peaks at about a redshift of 3 billion years after the beginning of the universe. And translating that into an actual empirical model that we can test on the right, anchored at both ends by measurements of the metallicity in the local universe and at the earliest stages of the universe where these heavy metals didn't actually exist, we can develop smooth models that connect these expectations, but our existing data, which is the blue data points and blue bands, which combines about 24 megaseconds of data at all spatial scales and, at large spatial scales and all redshifts, really does not allow us to constrain when in cosmic history the AGN were most efficient at enriching the intracluster medium between these two endpoints. However, with those 3 megaseconds of access-targeted follow-up, we will finally be able to discriminate between enrichment models in the early universe. So shown here, these data points represent combined constraints from these 30 systems between a redshift of 1.5 and 3. So this is an extremely exciting space as we push towards our next generation instruments and cluster catalogs to be able to constrain metallicity and its evolution to this degree. So the last point that I want to make is just the landscape of high redshift clusters and where we're going over the next couple of years for Axis to take advantage of. So shown here is a mass redshift plot of all of our SZ detections or Sunayev-Zeldovich cluster catalogs, where really we focused on the right-hand side of this plot, this upper diagonal in mass redshift space, which has provided us with a number of massive high redshift clusters that serve as pathfinder systems for next generation studies. I've already highlighted ACT 0123, but going to even higher redshifts, SPT 0459 and XLSS 122 their studies have all enabled us to determine what types of characteristics we need from our next generation X-ray instruments that are required to characterize the most massive systems at these higher redshifts. And these instruments and these cluster catalogs that are imminent and will be readily available over the next coming couple of years will be enabled by a dedicated multi-wavelength campaign. And so the number of clusters we'll have at these redshifts will expand by roughly an order of magnitude. So as we get initial detections of clusters from SZ and X-ray surveys, cross-matching with optical and infrared data from LSST and Euclid are going to give us an incredible number of clusters above redshifts of 1.5 that require high resolution follow-up. So they are primed for observations with access and complementary observatories like JWST. So I will end there and leave up my conclusions, but I hope I've left you with a bit of excitement on both measurements we can make of the intercluster medium and how that tells us a significant amount of information on AGN and star formation processes and their evolution in cluster environments, as well as specifically how Axis is going to make these measurements better than ever before and have incredible synergy with next generation cluster surveys as we go into the 2030s. And with that, I'm happy to take any questions.
Great. That was a really nice talk. So feel free to raise your hand. Richard, you want to ask a question?
Yeah, how much of the chemical evolution understanding and prediction depends on it just being relaxed clusters and not ones with shocks and other structure?
Very little. So the enhancement of the intercluster medium is a uniform property, and we can see that in the local universe that's consistent with relaxed and unrelaxed systems at large radii. With relaxed systems, you might see enhancement in the cores where those distributions can't be disturbed, but when we push towards cluster outskirts, that should be consistent regardless of relaxation state.
So you don't have to know if it's a relaxed or non-relaxed cluster for this work.
You do not know, but because of the high spatial resolution of axis, we'll be able to make morphological measurements at these redshifts that will give that information to us anyway.
Thank you.
Okay, Helen?
Oh, does that work?
Yeah, I can hear
Hey,
you. Yeah.
yeah. Let's see if I can turn the camera on. Hey, Anthony, that was an absolutely super talk. Thank you so much. Act 1, 2, is it 1, 2, 3? Looked really exciting. Can you tell me a little bit more about it? Is it like a strong cool cluster at redshift with 1.5? Is that it? Or I mean, it looks really symmetric and everything as well. And there's no point sources or anything.
There's no point sources in Chandra right now. So based on the analysis we've done with the existing Chandra and XMM data, this was not a targeted observation of this object for its dynamical properties. This came out of a larger high redshift massive sample that we were probing for evolution. But you're right. It does look very symmetric, very peaky in terms of surface brightness. The temperature of the core within the inner 7 kiloparsecs is about 3 keV. So we're still determining exactly the cool core structure of the object. So the analysis is still very much ongoing, but it's really been the Chandra data that's allowed us to characterize the nature of the cool core. No point sources within the cluster, at least from infrared, optical, and radio data that we can see. However, there is a pesky non-cluster member source that significantly contaminates the XMM observation. So that modeling has not been as fun or intuitive. But yes, at least for what we have with high spatial resolution, we're seeing a very symmetric, very beautiful cool core.
Fantastic. That's really super.
Great. So maybe I'll ask one more question. So, I mean, this is really nice work, and you can really see how you could, measure metal enrichment. I'm wondering sort of, maybe this is a little bit out of left field about cluster cosmology. I mean, when you have the temperature profiles, do you improve your mass measurements for clusters that much better that it matters? Or is it something that, having these types of measurements doesn't affect like the cluster mass and doesn't impact cluster cosmology or not?
It definitely will. One of just the anytime you are measuring the cluster temperatures in any bin, you're going to get an even better measurement of the gas density. And so having very finely spaced radial profiles of gas density is going to give you really accurate cluster masses within specific overdensities. So that will absolutely be helpful to us as we constrain the masses of clusters or the X-ray masses of clusters for use in cosmological studies. But there are also other cosmological studies that you can do. Specifically, I'm thinking about as we expand our sample of relaxed clusters at high redshifts with axis, you'll be able to do F-gas analyses at higher and higher redshifts, which specifically requires you to know very well the shapes of the mass and density profiles, as well as very tight constraints on the gas mass. So we have more relaxed systems, we have better constraints on the gas density and the gas mass, and all of those will help our understanding of cosmology.
Okay, great. Well, that